All right, welcome back everybody. In this video we are going to discuss material from section 10.12 of AP Calculus BC. We're going to talk about the Lagrange Error Bound. We're getting really close to the end of the course now, so I can see the light at the end of the tunnel. All right, so a couple of lessons back, I think it was section 10.10, we talked about the alternating series error bound, and it was very useful for us in determining the largest amount that the approximation could differ from the actual, the actual value to which the infinite series converges. One limitation with the alternating series error bound was that it only worked for alternating series, much as the name implies. In this lesson, we're going to introduce another method for finding error that works with any infinite series, okay? As long as we can get some information from that series. All right, and we start with Taylor's theorem with remainder. If a function has derivatives of all orders in an open interval, then for each positive integer n and for each x in the interval, f of x is equal to f of a plus f prime of a times the quantity x minus a plus f double prime of a over 2 factorial times the quantity x minus a quantity squared plus all the way up to the nth derivative at a over n factorial times x minus a to the n plus r sub n of x. Now, let's break this down, and I've got a little bit of narration down here below the box, but you should recognize that everything here is the Taylor polynomial that we worked so hard finding in the last section, okay? And then the only thing that we need in order to make this exactly the function, we need this remainder. There's always a remainder that if we added it to the polynomial, we would get the actual function, okay? And furthermore, we know that this remainder is equal to this right here. It's equal to the n plus first derivative, the next derivative after our polynomial, evaluated at some value c, that's between a and x, all over n plus 1 factorial times the quantity x minus a to the n plus 1. So this looks a whole lot like the next term of this polynomial. The only difference between this and what would be the next term of this polynomial is this factor right here, the n plus first derivative at c. Because this is the n plus first derivative at a that we're using in all of these coefficients. C is a different value, okay? And we really can't tell what it is. You know, I say here, well, this formula for the remainder looks really nice. It's impossible for us to find the exact value of it because we just don't know which c produces the actual remainder. What we can do, though, is we can come up with the maximum possible area because we can find the maximum possible value that this could have. And then the remainder needs to be less than or equal to that value, which means that we've put a cap on the error by using this remainder. Okay? How are we going to find our cap? Well, we're going to use what's known as the Lagrange Error Bound. Okay? The remainder, this remainder term that we see right here, which is equivalent to the error, has to be less than or equal to the maximum value of the absolute value of the n plus first derivative of f at c. So if that's negative, we're going to turn it positive to bound the error. The maximum value of the absolute value of x minus a to the n plus first. That's, usually we're talking about the distance from x to the we're talking about the distance from x to the center of the series. So we're going to have some maximum value on a given interval. And we're going to divide all that by n plus 1 factorial. All right? So if we can find all of these pieces of this, we now have a boundary for the maximum possible error that could occur. And that is our Lagrange error bound. So this formula right here is going to be super duper important for you. All right, let's go ahead and talk a little bit more about this, and then we're going to put it to use. So it says here, the toughest part of evaluating the Lagrange error bound is determining the appropriate value for the maximum of this, oh, I forgot my absolute value signs there, of the absolute value of the n plus first derivative of f at c. I guess my absolute value should be around there. Oops. Got a little overzealous there. There we go. We'll do this in one of two ways. If we have a graph, we'll be able to look at the graph and find a clear bound for the interval. We may not be able to find exactly, the precise one, but we can always take a larger value on the graph and use that as our boundary. If our function is a sine or a cosine function, the largest possible value of any of the derivatives of the sine or cosine function is going to be whatever, maybe a constant might be there, but the maximum value of sine and cosine is 1, and we can use that to our advantage to bound anything in where the n plus first derivative is a sine or a cosine. We might find the derivative of f algebraically, and then we can find the max value of it on the interval that we're working with. Or the last thing, we could actually be told the maximum value of the derivative on a given interval, and then we can go ahead and use that. All right. Let's go ahead and take our first stab at the Lagrange error bound. The approximation natural log of the quantity 1 plus x, which is approximately x minus x squared over 2, is used when x is small. Find the Lagrange error bound when the absolute value of x is less than or equal to 0.1. So first of all, we need to figure out what error bound we're looking for. Okay? Since this is a second degree Taylor polynomial, we're looking for the second degree Lagrange error bound. So the error which we're going to approximate with the second degree error bound is less than or equal to the maximum value of the n plus first derivative. So we're looking for the max of that times the max of absolute value of x minus a to the n plus 1 all over n plus 1 factorial. Oops. I could have filled in more information here. We know that we're looking for the error bound for the second degree polynomial, so I can replace this n plus 1 up here with a 2 plus 1, which is 3, and I can replace the n plus 1 in my denominator also with a 3. Okay. All right, let's see. Now I just need to figure out what these other pieces are. Now the maximum value of the absolute value of x minus a is the biggest value that x can take on the interval. We can see where this interval is centered. This interval is centered at x equals 0. This is a Maclaurin series. This interval is centered at 0. And if we're trying to find the error bound on the interval from negative 0.1 to 0.1, the biggest possible distance between x and a on that interval is just going to be 0.1. And so that max of absolute value of x minus a to the third is just going to be the maximum possible distance. Now with Maclaurin series, it's really easy to see what that maximum possible distance is, because it's just going to be, the endpoint of the interval is going to dictate where that is. And then the other piece I need is the maximum value of the third derivative of f on this interval. Okay, so let's find the derivatives of f. Here's our function. And when we talk about the derivatives of f, we're talking about the function, not the polynomial approximation. If we took the third derivative of this polynomial approximation, it would always be 0. So we want to make sure that we take the third derivative of the original function. So f of x is equal to natural log of 1 plus x, so f prime of x is 1 over 1 plus x. F double prime of x is equal to negative 1 over the quantity 1 plus x, quantity squared. And f triple prime of x is equal to 2 over the quantity 1 plus x, quantity cubed. All right, now we're finding the maximum value of this third derivative on this interval right here, the interval from negative 0.1 to 0.1. So imagine what happens when we substitute values of x into this denominator. When we have x equals 0.1, it would be 2 divided by 1.1 to the third power. If I put 0 in here, it would be 2 over 1 to the third power. If I put negative 0.1 in here, it would be 2 divided by 0.9 to the third power. Now, if you think about what you know about fractions, when we're looking at fractions, the smaller the denominator, the bigger the fraction. So we want the value of x that makes this denominator as small as possible. And that is the value that we get when we put negative 0.1 in here. And so the maximum of the error is going to be 2 over 0.9 to the third power. All right, and now we are going to calculate the error here. All right, and so we've got 2 over 0.9 cubed times 0.1 cubed divided by 3 factorial, which is just 6. And I get as my error 0.000457, etc., etc. Now, I want to keep 3 non-zero places, so I'm going to keep those last 3 digits, 457. But we talked about this a little bit when we did the alternating series error bound. When we're talking about error, we always want to round this decimal representation up, because the maximum error that we can have here is 0.0004572, etc., etc. 0.000457 is smaller than that, and therefore our error could be bigger than that value if we rounded it off there. So we're going to round it up, and so this is going to be 0.000458, and that is rounded to 3 non-zero decimal places, and that is going to be our Lagrange error bound for example number 1. All right, I took a lot of time going through the facets of this first example. I'm going to go a little quicker in the future examples. We're going to call it quits for this video, and we'll come back and do a second video where we do more examples related to the Lagrange error bound. Until then, have a great rest of your day, everybody, and we'll see you next time. Bye-bye for now.